Okay, imagine this. You've got a machine worth hundreds of millions of dollars, and it's hurtling through the vacuum of space. Then, all of a sudden, something goes wrong. You can't just send out a mechanic, you can't touch it, but you absolutely have to fix it, like right now. Well, that is the incredibly high-stakes world of satellite operations. And today, we're going to dig into some amazing new research on how you diagnose a machine from millions of miles away. Let's get into it.
So let's just dive right into the core problem. Satellites are, without a doubt, some of the most complex and, well, isolated machines we've ever built. And when one of their critical systems starts to fail, the stakes are enormous. We're talking lost communications, failed science missions, or even losing the entire satellite for good.
Now, what's really wild is how specific these failures can get. This research points out that a staggering 38% of all malfunctions in a satellite's attitude control system, the system that keeps it pointed in the right direction, are caused by just one type of component: reaction wheels.
So, what in the world are reaction wheels? Well, think of them like these super sophisticated flywheels deep inside the satellite. By spinning them faster or slower, the satellite can adjust its aim with pinpoint precision, all without firing a single thruster. They're basically the satellite's sense of balance, which makes them absolutely critical for everything.
And that brings us right back to the central challenge for every aerospace engineer out there. When one of these wheels starts acting up, you can't just pop the hood and swap it out. This one single question has been the driving force behind decades of work in remote diagnostics. How do you figure out what's wrong from a control room back here on Earth?
So, how have we traditionally tried to tackle this problem? Well, historically, there have been two main strategies for dealing with these faraway failures, and each one has its own set of pros and cons.
Okay, so the first approach is pretty much what it sounds like: hardware redundancy. It's the brute force method. You just pack a bunch of spare parts. If one breaks, you just flip a switch and turn on the backup. It's reliable, sure, but it's also incredibly expensive and adds a ton of weight. The newer, smarter approach is called analytical redundancy. The idea here is to use intelligent software to keep an eye on the hardware you've already got, trying to spot and diagnose problems before they become catastrophic.
So how does this smart software actually work? Well, one of the most popular ways is this model-based approach, and it's actually beautifully simple. First, you have a software model on the ground that predicts exactly what that reaction wheel should be doing at any given moment. Then, you compare that prediction to the actual real-time data streaming back from the satellite. And if there's a big gap between what should be happening and what is happening, engineers call that a residual. Boom, an alarm goes off. You've likely found a fault.
But here's the catch. Space is a really noisy place. You've got radiation, huge temperature swings, all sorts of things can create static or noise in the data. And that noise can trick the system into thinking there's a problem when everything's actually fine. You get a ton of false alarms, and that's a huge headache. This is where the old models just aren't quite enough, and it opens the door for something much more powerful: AI.
So, you might be thinking, just throw some AI at it, right? I mean, on paper, it seems like the perfect fix. AI is designed to find tiny patterns in super complex data. But when you actually try to apply it to this problem, you find out that AI has its own unique blind spots.
We all know that AI and machine learning are just incredible at pattern recognition. You can feed them these massive data sets, and they'll learn to spot anomalies way better than any human or simple model ever could.
But, and this is a big but, what happens when the data you're working with is the exact opposite of what AI likes? The data from a satellite isn't clean. It's not perfectly labeled. And most importantly, it's not abundant. You just don't have thousands of examples of satellites failing in the exact same way. The data is scarce, it's messy, and it's unpredictable.
This research really nails down 4 big reasons why your standard off-the-shelf AI just doesn't cut it here. First, that data dependency is a killer. There just aren't enough real-world examples to train on. Second, a lot of these models just aren't fast enough for true real-time diagnosis. Third, they often ignore the fact that the satellite is actively trying to correct itself, which messes up the data. And finally, they can overfit. They get too good at spotting the fake practice faults engineers feed them, and then they miss the real, weird ones that pop up in space.
So, if the old models are too simple and standard AI is too picky about its data, what's the solution? Well, this is where the research gets really brilliant. The authors proposed a hybrid framework, one that combines the very best of both worlds. It takes the physics-based knowledge from the old models and merges it with the incredible pattern-spotting power of AI.
The first piece of this incredible puzzle is what I like to call a fault simulator. They took a super detailed software model of a reaction wheel and used this clever statistical trick called a Markov jump strategy. What that means in simple terms is that they could make the model randomly jump between different kinds of failures over and over again. It's like having a virtual satellite that you can break in a million different realistic ways, which generates a nearly infinite amount of perfect training data for your AI. So, data scarcity, problem solved.
The second component is a signal purifier. Now, the name for this thing is a mouthful, a Markov jump-adjusted particle filter, but what it does is actually pretty easy to understand. It acts like a super advanced noise-canceling filter. It intelligently cleans up all that messy, staticky data coming from space, so the AI has a pure, clean signal to analyze.
And finally, you have the real-time detective. This is a custom-built deep learning model, and the key is its sliding window design. Instead of trying to look at a huge chunk of data all at once, which takes time, it analyzes tiny, overlapping snippets of the data stream as they come in. That sliding window is the trick that finally cracks the code on doing this diagnosis in true real time.
Okay, so the theory is fantastic. You've got a simulator to create the data, a purifier to clean it, and a detective to analyze it. But the big question is, did it actually work when they put it to the test?
Well, the results are seriously impressive. Under low noise conditions, this new framework was able to spot faults with an accuracy rate as high as 99%. I mean, that is just an incredible level of precision for a problem this complex.
But, good science is always about honesty. And the researchers pointed out something really fascinating. They found that when they tried to use the signal purifier and the real-time detective together, they were actually a bit incompatible. It was almost like they had different opinions about what a fault looked like.
So what's the bottom line here? The big takeaway is that even if these two components don't work perfectly together yet, the individual tools they built are a massive leap forward. Both that signal purifier and the real-time detective proved to be incredibly powerful and effective on their own. They're game changers.
This research really does light up the path forward. What we're looking at here isn't just a better way to find problems. It feels like a foundational piece of a much, much bigger puzzle. I mean, could this kind of high-accuracy, real-time diagnostic tool be the first step toward creating satellites that don't just find their own faults, but maybe even fix them all on their own? The answer to that could literally change the future of everything we do in space.